Accelerometers don't have incorrect intuition. They just spit the truth. If you have an object initially at rest and then let go, you can be sure that it's going to fall. Isaac Newton told me that this is due to the force of gravity, and I understood this. But then Einstein came along and ruined everything. He told me that gravity isn't a force, it's the bending of space-time, and I didn't understand. People tried to help me by coming up with demonstrations like this, where they take a fabric that represents the fabric of space-time, and then they put a heavy mass on it that bends the space-time. And sure enough, another object is attracted to it. But this made me even more confused. If this is space-time, then what's the space-time bending into? What's all this space above and below it? And the most obvious problem, gravity is the thing pulling the heavy ball down, stretching the fabric. You can't use gravity to explain why gravity works. So in the end, I was left wondering, if gravity isn't a force, then what's actually making the object start moving in the first place? Why do I feel like I'm accelerating when I'm standing on the earth, not accelerating? But then when I'm falling toward the earth and actually accelerating, I'm not? Why do I feel like I'm accelerating when I'm standing on the earth, but then when I'm falling toward the earth and actually accelerating, I'm not? Last night I woke up in the middle of the night and finally understood. I understand Einstein's field equations. To understand this, we're going to keep it simple. Let's pretend that there are only two dimensions, one space dimension and one time dimension. So instead of x, y, and z axes, we just have a time axis and a space axis. When the axes are straight lines like this, it represents flat space-time. If a person is just standing still with no velocity, then they'll move up in a straight line on this graph here. This is because they're only moving through time and not space. If they have a velocity, they'll be moving in a tilted straight line because they're always moving forward through time, but also through space. And then if they're accelerating, it'll look like a constant curvature. Now let me show you what happens to these lines when something with mass is introduced. Now let's say I have something with a lot of mass like the Earth. Well, in this case, it's a one-dimensional Earth. And it's stationary, so from its worldview, it's just moving in a straight line through time. But because it has a lot of mass, it actually does something to the graph itself. It bends it. Here's a view of the bending on both ends of the one-dimensional Earth. Now notice something about this bending. It's only bending the time axis, not the space axis. Notice how all the time lines have curvature to them, but all the space lines are completely straight. The physical meaning of this is that clocks that are closer to something with a lot of mass tick slower compared to clocks further away. But rulers near something with mass don't shrink nearly as much. The geometry of time is about 1 billion times more distorted than the geometry of space near Earth. So that popular picture of gravity as warping this fabric of space-time is wrong. Well, not wrong, but the original depiction was meant to represent the fabric of space at one specific moment in time. It wasn't meant to show space and time because time bends much more than space. And the bending of space has nothing to do with why something falls. Which means that spandex sheet demo I did at the beginning is pure baloney. So how does the bending of time make something move toward Earth? You can see this by taking our stationary object that's just sitting in space, only moving through time. Remember, stationary objects just move straight vertically through time. You can almost think of it like it has this innate momentum carrying it straight, and it won't deviate from that course unless it hits something. But now let's put it near the Earth and watch what happens. Because of the skewed graph, the object inevitably moves through space as well as time. So there's no sudden momentum gained or anything, but the skewed coordinates made it start moving through space while moving through time less. But that's not how we perceive it, because we perceive flat space-time. So then let's see what this black straight line looks like in flat space-time, which is how we perceive things. It's curved exactly in the same shape you would get when something's accelerating. So that's why we perceive something as accelerating towards Earth when it's falling. This flat space-time view isn't correct, but it is intuitive. Because on our small scale, space-time is essentially flat. It takes a lot of mass to noticeably bend time. Other than the Earth, nothing in our life is big enough to bend our local time. So we think in flat space-time. And that's okay for almost everything that we do in physics. So it's okay if you don't want to call gravity bent time, just call it a force and it still works out just fine most of the time. But with this view of the bent axis of time, it will help us finally understand why my accelerometer says I'm accelerating when I'm standing on the ground, but not when I'm in free fall. You can try this yourself on your phone. Get any app that shows you the accelerometer data from your phone. So this is telling me that when my phone's just sitting on the ground, it's accelerating. And sure enough, if we look at the graph of something sitting on the surface of the Earth, it has a constant curvature. But notice that while sitting on the surface of the Earth, the phone isn't moving through space. As you can see on the graph, it doesn't cross any space lines, but it is accelerating. So acceleration is defined as any time we don't move in a straight line in space-time, no matter whether or not the space-time is bent or not where we are. So in general relativity terms, this rubber chicken is not accelerating, but the drone that dropped it is. So the ground is dragging you through space-time right now, deviating you from your natural straight line course. That's why you feel an acceleration, or in other words, that's why you feel a force against the ground, or feel the weight of your body on the ground. But as soon as we don't let it touch anything, like when we toss it into the air, as soon as it leaves my hands, the acceleration drops to zero, because the Earth isn't accelerating it anymore and it's just moving through time. Accelerometers don't have incorrect intuition. They just spit the truth. They just spit the truth. So if I were in true flat space-time and started accelerating in a rocket ship, it would look like this. And when I'm just standing on Earth, it looks like this. They're the same path, the same thing is happening. This is called the equivalence principle. There's absolutely no way to distinguish acceleration in flat space-time in the middle of space from the pull of gravity while standing on Earth. We can't distinguish between them because they are the same thing.